So we're going to start with a very simple example of y equals x. And we're going to look at the area between y equals x, the x-axis, and a line x equals 5. So if we were to revolve this around the x-axis, what shape would we get? Well, I hope that we can all envision that this would be cone-shaped, and we'd have a whole bunch of these little discs revolved around like this. And this is the disc right here, my very crude drawing that I've pulled out right here. And how do we find the volume of this disc? Well, the volume of a thin disc is going to be pi r squared times the height. This is really just a really short cylinder. And what's the radius here? Well, the radius here is x. That's our function value. It's f of x. F of x is equal to x. So our area or our volume of this disk would be pi times x squared times the height of the disk. And if I call that height delta x, we have this. So what we're going to do is we're going to add up a whole bunch of these things from x equals 1, or from x equals 0 to x equals 5. And just like with area, the thinner the slice, the better our answer is going to be. We're going to be closer to the true area because, well, if we are really doing this, we're really finding a rectangular area in here that we're revolving around the x-axis. And that's not really what's happening. We got this slice cut off here. This is really angled in. But if we make it really, 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 really thin, effectively, it's rectangular. So what's happening here is, just like before, we're going to take the limit as n goes to infinity of the sum from I equals 1 to n of pi ri squared times delta xi. And what we get then is the integral from a to b, where a is where we're starting this and b is where we're ending this, of f of x squared, because f of x was the radius of this disk. And as delta x gets really small, we call it dx. And of course, we have to multiply by pi because this is a circular disk that we're going with. But what about if this volume isn't being revolved around the x-axis? What if this volume is instead being revolved around the y-axis? Well, the volume is going to be similar. It's going to be pi times a to b of f of y dy, and f of y is getting squared. Now, in other words, what's happening here, the difference between these two, f of x is our y equals something, and that something is what's going here and getting squared, and this is x equals a and x equals b as the limits of integration. If we're revolving around the y-axis, we're differentiating with respect to y, so this thing that I have called f of y here, we're really taking our equation, our function, and solving for x. That's the thing that we're squaring, and our limits of integration are going to be y equals a and y equals b. And we'll do an example with this in just a moment, but I want to go back to the one that we watched a video for. So this was the region that we have. We're rotating this around. How would we find the volume of this disk? Well, we've done some problem solving with circles probably at some point. If I wanted the area of this circle with the hole cut out of it, it would be pi r1 squared minus pi r2 squared, where r1 is the big radius and r2 is more than just a friend to C3PO. R2 is the radius of the small circle here, and we take the big circle area minus the little circle area. We've got the area of this part out here, this washer. But since we're finding volume, we have to take that area of the disk times the height, which I've called delta x. And of course, we're going to add together a whole bunch of these little disks all the way down. So what we're getting is this formula. So we're taking the limit as n goes to infinity from 1 to n of pi r1 squared minus pi r2 squared times delta x. And taking that limit converts this into an integral with our dx. So we have pi times the integral from a to b of f of x quantity squared minus g of x quantity squared. Those are my two radii. And we're differentiating with respect to x. And this is going to be true where f of x is greater than g of x for all x on the interval. And a and b are the x coordinates of the point of intersection. So, what we're doing, let's revisit this. We're finding a whole bunch of little strips in our graph, and then we're revolving them all around to create this washer. In this case, there'd be a hole in the middle, like so. And these slices are what we're going to add up. We're going to add together a whole bunch of these little washers, and those things put together, because these washers are so small, they have an infinitely small thickness, that finds us the volume of this revolution. And now, let's do some examples. So, find the volume of the solid created when y equals square root of x, in x is an element of 1 to 4, is rotated 2 pi radians around both the x-axis and y-axis, of course, done separately, not at the same time, because that would just be absolutely ridiculous. So, volume around the x-axis, volume equals the integral from x equals 1 to x equals 4, square root of x dx, and of course we're squaring our f of x value. And don't forget to multiply by pi. I can remember back in high school, I always forgot to multiply by pi. Don't you be like me, be better than me, which we all aspire to do. So volume equals pi 1 to 4 of x dx. That's going to be pi times 1/2 x squared, evaluated at 1 and 4. So pi times 8 minus 1/2, and that's going to be a total volume of 15 pi over 2 cubic units. And remember, the formula we're using is volume equals pi integral of y squared dx, and this y squared is a function of x. It's not really a y anymore. We're putting x's there. It's weird, right? But we know what we mean by that. That is a function of x. So part B, now we revolve around the y-axis. Well, there's a couple things we got to change. We have to rewrite our function. Volume equals pi times the integral of, okay, so if y equals x squared, x is equal to y equals square root of x, x is equal to y squared. So y squared squared dy. But we're not going to integrate from 1 to 4. Well, we need to write an interval for y. Y is an element. Okay, so if I put 1 in for x, then y is equal to 1. If I put 4 in for x, y is equal to 2. So you have to change the limits of integration here, ladies and gentlemen. That's something you have to be careful with. So pi times the integral 1 to 2 of y to the 4th dy. That will be pi times 1/5 y to the 5th, evaluated at 1 and 2. And this becomes pi times 32 over 3 minus 1/5, which simplifies to 31 pi over 5 cubic units. So again, this volume formula is pi times the integral of x squared dy, and it's not really x's, it's x equals y like we had right there. One more example to look at today, and it's for when we're between two curves. So we have two graphs, x equals y to the 4th over 4 minus y squared over 2, and x equals y squared over 2. these two curves completely enclose a region, we're told. Find the volume of the solid when this region is rotated 2 pi radians around the y-axis on the interval from C to D, where C and D are greater than or equal to 0. So we don't even know the region that we're integrating from, the values of, in this case, y. Because these are both x equals, these limits of integration, we need to find that y is going to be an element in there. So we need to find the points of intersection. Well, how do we find points of intersection? We equate these two things. And we can solve this equation. We're going to get y to the 4th over 4 minus y squared equals 0. Factor out y squared. We get y squared over 4 minus 1 equals 0. Y is equal to 0, or y is equal to plus or minus 2. So what we're looking for is we're looking for the interval from, we want y to be on the interval from 0 to 2. We're told that C and D have to be positive. We're integrating from y equals something to y equals something because these functions are x equals, and we're revolving around the y-axis. Okay, so how do we do this? Volume equals pi integral 0 to 2. We're going to take, I don't know which function is above which, and these are x equals, not y equals. Oh my gosh, I don't know what I'm going to do. Well, remember what we did with area. There's an easy way around this. It doesn't matter which one is above it if we take the absolute value. Aha! Beautiful. So it's going to be, I'm just going to take the bigger one and put it first, the thing that's more complex, not necessarily greater. Y to the 4th over 4 minus y squared over 2. We're squaring that, subtracting the other function, and that squared dy. Whew, that's a big one. But it's not so bad. We can deal with this. We've got pi times the absolute value, integral 0 to 2. We're going to simplify what's inside. We square the binomial. We combine like terms. And we're going to get y to the 8th over 16 minus y to the 6th over 4 dy. And that is something that we can integrate. So pi times the absolute value of y to the 9th over 144 minus y to the 7th over 28. Absolute value of that evaluated at 0 and 2. And we get pi times the absolute value of 2 to the 9th over 144 minus 2 to the 7th over 28. And of course we're doing minus 0 when we substitute our lower limit. And simplifying this, we get 64 pi over 63 as our volume from 0 to 2 on the y-axis. And that, ladies and gentlemen, is where we stop. Have a great, great time.